Hello, good people. Here we go. We're doing number three. Is this an alternating series? If it is, can I use my two conditions to check for convergence? When I look at number three, I notice this part will produce the alternating part. So this is an alternating series. So we're going to start with the first condition. We're going to take the limit as n approaches infinity of n plus 7 over n. Well, wait a minute. If I do this, that means my limit is actually 1. That does not equal 0. So therefore, the alternating series test doesn't work, is inconclusive. So I got to find another way to do it. How do we do it? I don't know. But the alternating series test is not the way to do it. That's all we can say. And we'll find another way, maybe. I don't know. But that's the end of our story here. Now, sometimes we look at a setup and it looks like an alternating series, so you want to use the alternating series test. So again, be aware the alternating series test, those two conditions that have to be met, only work if the series is alternating. And when I look at this, I see the device right here. Yeah, that's what causes an alternating part, right? But I also notice this. So what happens when I substitute 1? Well, when I substitute 1, I'm going to get negative 1. When I substitute 1, I'm going to get cosine of pi, of 1 pi, which is negative 1, times 1 over 1 squared plus 1. And I believe that's 1 half. That's positive. Plus, when I substitute 2, I'm going to get negative 1 squared times cosine of 2 pi, but cosine of 2 pi is 1 times 2 over 2 squared plus 1, and that's going to give me 2 fifths. Plus, when I substitute the 3, that's going to be negative 1 to the third power, that's negative 1, times cosine of 3 pi, that's negative 1, times 3 over 3 squared plus 1, and I believe that's 3 tenths. Is this an alternating series? No. So the alternating series test does not apply. I can't even start to take the limit to see if it equals 0 because it's doesn't even work. It does. This is not that type of series. Does not apply. So then I would have to find another way. What is that other way? I don't know. Well, if this and this are always going to produce a positive answer, then I guess I could say that this series is equivalent to this series. And if you've watched the previous set of videos, we said we could use a limit comparison or a comparison test to figure this out. I believe this will be a divergent series if you use the limit comparison test with a buddy series, if you will, of 1 over n of the harmonic. I think you can figure that out. So the moral of the story is it's not an alternating series, so I can't even check my two conditions. I got to try something else. Da-dee-da-dee-da-dee. Let's see. What else can we do? Ooh, how about number 2 here? The alternating series test can be used to show the convergence of which of the following alternating series? Let's see. Is this an alternating series in Roman numeral 1? Yes. And what is a sub n? A sub n is 1 over n. Is the limit approaching 0? The limit is n approaching infinity of 1 over n. Is it 0? Yes. Is 1 over n decreasing? Heck yeah, it is. Check. Okay, so number 1 works. That means I can scratch out B, I can scratch out C. So let's keep going. Well, I guess we can check number 3, right? Because if number 3 works, then it has to be this one. It can't be this one. So let's check number 3. Is this an alternating series. Yes, I see the alternating part. So we're going to take the limit. So the limit as n approaches infinity of the term here, is that going to 0? Well, no, this is going to give me 4/5. That's not equal to 0, so I don't know what's happening. So I can't use the alternating series test to show convergence there. So that means this is out. Okay, well, that didn't help. How about Roman numeral 2? Is this an alternating series? Yes. Can I take the limit as n approaches infinity of n over n squared plus 4? Does that equal 0? Yes. Is it decreasing? Well, can we do what we did before? A sub n plus 1 times, I'm sorry, divided by n over n squared plus 4, which is the same thing as multiplying by its reciprocal. And the question is this going to produce something that's less than or equal to 1? Will it produce something that's less than or equal to 1? I don't know. Let's multiply it out. So n cubed plus n squared plus 4n plus 4. In the denominator, I have to multiply this out first. N squared plus 2n plus 1 plus 4, I guess I could just say plus 5. And then multiply n out, n to the third plus 2n squared plus 5n. Can I show that the denominator is bigger than the numerator? Because if I can, that means it's decreasing. And if it's decreasing, it passes the alternating series conditions to show that that is the case. Yeah, I guess I could. Oh, by the way, now I just saw something that I hadn't seen before. But let's continue. Um, let's see. Can I do the same trick I did before? N cubed plus n squared plus 4n plus 4. And then in the denominator, I can have n cubed plus 1 of the n squares. I still have another n square over here. And I can do plus 4n, and then I still have another n here. So so as you can see, this part of the numerator plus 4, I have the same part of the numerator here plus this extra. Well, this extra is going to be bigger than 4 as n gets bigger, so this is decreasing. This is less than 1. So therefore it's decreasing, and I can do the alternating series test to prove convergence for Roman numeral 2. All right. This set of videos was the first time where we saw a series, a sum of infinite number of terms, where the terms were changing signs. That's the alternating part. The alternating part can be used or can be caused by a device like this, or like this, or a cosine, or a sine of pi over 2. We can cause that. We can prove that an alternating series test converges by checking these two conditions. Does the limit equal 0? And is the sequence of terms decreasing? If I can show that those two things are true, then I know that that alternating series converges.